Now let's introduce another fundamental data structure called a graph. So mathematically, graphs are considered a collection of nodes, or probably more commonly referred to as vertices, and edges. So what does this mean? If I'm drawing a picture, then these circles here are the nodes, and the lines between them are the edges. All right, so that's a node, there's an edge. So what are the real world applications of this? Well, certainly any kind of network can be represented as a graph. Maybe these are computers and these are the wires between them showing which ones are directly connected. The internet can be represented as a graph. Strictly speaking, the internet and the World Wide Web aren't the same thing, even though many people use the terms synonymously, but World Wide Net, or web, excuse me. So what's the difference? The internet is the physical connection, consists of computers and wires. The World Wide Web is more of a virtual network. This web page, if I have one web page, page 1.html on one website, then might have a link to, page 2.html on another website. So that's the World Wide Web. So the entire World Wide Web can be represented as a graph. But even other things can be represented as graphs. Things like, let's say these are cities. So city 1 is connected to city 2, which has a road to city 3. There actually might be many roads, and so forth. So there are many real world things that can be represented as graphs. Now there's lots of types of graphs depending on how we represent the connections and things like that. Let's look at a few of the basic ones. So we have directed and undirected graphs. So directed means it has arrows indicating a direction. All right. Undirected then means there are no arrowheads. So this is undirected and directed. If the nodes here represented intersections in a city, so it really would be more rectangular, right? So these are the city streets, and this is where there's an intersection. Well, in most cases, they're undirected because traffic can go in both directions. But if I had one-way streets, in particular if I had a lot of them, well, then I might use arrowheads to indicate I can go from here to here, but not the other way around, something like that. So that's one possibility. Another way to describe graphs is as being weighted and unweighted. If we go back to my example of the World Wide Web, typically that would be represented as unweighted because we would simply say this web page connects to this web page, which connects to this web page, and so forth. And where the weights would occur at would be on the lines, the edges. But we just say, well, they're connected. It doesn't matter about having a value associated with that. But if there is a value that we would use, then we would typically have weighted. So if we go back to my example of the cities, you might say, well, this is 40 miles, and this is 42 miles, and say this is, 35 miles, and 30 miles, and 33 miles, and so forth. So these will be the weights, 42, 40, 35, 30, 33, and something over here. We'll say it's 30 as well. All right? So those are weights, but in many cases, the way you represent a connection is simply 0 meaning there's no connection and 1 meaning there is a connection. But the 1 isn't the actual value. It's just a binary representation. It's connected or it's not connected. All right? So these are graphs, and they have many practical uses. And you can, in fact, take an entire course on graph theory, which typically would be taught at a graduate level. But this is a mathematical representation or an abstraction here. So how would we represent them in my computer? Well, there's two basic ways of representing graphs on a computer. And those are the adjacency matrix and the adjacency list. All right? So let's say I have this right here. I have this graph. I have A, and we'll make it directed. B, C, D, and D goes to C, and D also comes back to A. All right? Well, adjacency matrix will be represented as a two-dimensional array. So the matrix form will be like this, and I'm going to make the rows be the source, and then the columns will be the destination. And let's even do this. We'll have B comes back to itself, because those types of things occur at times. So you could swap these, but you need to be clear on which one you think it is. So what this says, we'll make this A, B, C, D, and these will be columns A, B, C, and D. Since I don't have weights here, I'll use a 0 to indicate no connection. So from B to C, it would be 0. But when there is a line going between them, we'll say this, then I'll use a 1. So does A connect to itself? No. Does A connect to B? Yes. To C? Yes. To D? Yes. So now B, does B connect to A? Well, no. A connects to B, but since it's directed, B doesn't go the other way. Does B go to itself? Yes. To C? No. To D? No. And now C, does that connect to any of them? Not as a source. And finally, D goes to C and A. So this is the adjacency matrix for this. And then in two-dimensional array terms, that's the first row, and then you come down and finish it up. So this is how you do it in the computer. So what's the problem with this? Well, remember, I said that one of the graphs that you could represent would be the World Wide Web. But there are literally billions of web pages. So if I try to represent it like this as an adjacency matrix, I would need to have, well, in excess of 1 billion rows and 1 billion columns. So that means I'm going to store 1 billion times 1 billion numbers. That's a lot of numbers. In fact, it's going to be too big for whatever you would want to do. And in fact, most of those would be zeros, because you think about it, even the most connected web page in the world is still not connected to very many other web pages in a percentage sense, right? Out of the billions of possible web pages it could be connected to, it's not connected to many of those. So instead, what you do with an adjacency list is you basically keep track, so this will be my source, of which things you're connected to only. So A goes to B, C, and D. And this is row for B, so B goes just to B itself. C goes to nothing else, so we'll say that's null. And finally for D, goes to A and C. So now if I want to figure out what this looks like, I can just work down to a row. And like I said, this column these are the source nodes. And then this would be a bunch of destination nodes. All right? So those are two basic forms. So let's look at some code that actually implements this. So what we're going to use will be, in my first program, will be this graph right here. So A goes to B and C and D, and B goes to C and E. C doesn't go to anything. D goes to itself, F and G. E goes just to H. F goes just to E. And G goes to H. That's what we'll use. So let's see how I implemented that. So here I use a pound define. If you haven't seen my hash table video in which I tell you what this is, it's a preprocessor directive, just like pound include is a preprocessor directive. There's a tool called the preprocessor. And when I say I want to compile C89 graphs matrix here, before the compiler actually gets to do its job, the preprocessor goes through and does some things. Pound include says, oh, include this .h file for me so I know what printf means when you encounter it. The pound define says everywhere you see the word size, replace it with the number 8. So this is not a variable. I can't change this. It's just doing a search and replace. So by the time that the compiler sees it, down here for example, where I use it, it's equivalent to I just had put this in there, 8. So what's the benefit of it? Well, I use size in a whole bunch of places. And I also capitalize it. I don't have to capitalize it, but I do so to make it stand out as probably not being a variable. So if we look at these different places, in fact, let me do this. If you haven't seen my video where I get you up to speed on Vim and Linux tools, I talk about grep. In fact, I just barely touched the surface of what all these things do, but let's look for within this file. So this says search for this word, size, within this file, and there's all the occurrences. So there's where I define it, so I use it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different places. In fact, I could count that actually. It says 11 because it includes this, right? So I just piped it. That's the vertical bar. It's a pipe, so it sends the output from this command as the input to this command, WC, which is short for word count. And then L, the dash L says count the number of lines because there's lots of other options. So that's what I did there. So how does this work? So I'm going to have labels here associated with what I have here, and I've spaced it out to make these also column labels so it's clear. And then here's some comments that indicate which row is which. And this represents this graph. So A goes to B, C, and D. A goes to B, C, and D. B goes to C and E. B goes to C and E. So see, that's the same thing. So there's my graph represented as an adjacency matrix. I'm going to use this in a moment to indicate whether or not I visited a node, because I'm not only going to print out which nodes are connected, but I'm also going to use a depth first search to process it. If you saw my video on binary trees, trees are actually a special case of a graph. In trees, you have a starting node that we typically draw at the top called a root. And then they're also directed graphs in which you're working down, but you never merge back into each other. Graphs, we don't have those same restrictions. You can start on any node. You may choose to have, like in this case, A can go to B, and A could go to C, and then if I had another arrow here, C could come back to E, so I can split and then come back together. In a tree, even though you don't draw the arrows, this is really what it means. The parent goes to the children, or at least that's how we often think about it. Traversing, you can go both ways. But here's the root, and then you typically think of working like this, in this direction. But it is technically a special case of a graph. So I showed you how to do a depth first search of a tree, but we can apply it to other graphs as well. And we also could do breadth first searches. So let's see how this works. Let's run the code first. And so it shows what's connected to what. A is connected to B, C, and D. B is C, E. C doesn't go to anything. D goes D, F, and G, and so forth. Let's look at the code on that. So I'm going to use this when I come down here for this visited part for depth first search. But all this does is initialize this. And then I'm going to have a function that resets it. Because I did have some other code here before, so I was actually using it multiple times. So all init does is go back through that array and reset everything. So let's see how to print the graph. So I'm going to start with row R, print the label that corresponds to this, which is how I get A here. And then when I'm talking about row A, then I go through every column in the graph, because I pass in the graph right here. And if the connection is not equal to 0, that means there is a connection. So if the value is not equal to 0, excuse me, then I print the label that corresponds to that column. So that's how I print all this. So that's all there is to that. But then I do a depth first search right here. So let's see how that works. So let's do it on paper and then come back and see. So what I've written, I'm going to copy this over to my paper so you can see it here. But there we can see that we have A, B, C, E, H, D, F, and G. So how does that work? So I'll start with A, and the way I'm making decisions as to which of the paths to follow, I just do them in alphabetical order, because that's the way they are on the labels. So that means I go to B, and when I get to B, I have a choice between C and E, but C comes before E, so I go down this path. And now C doesn't go to anything. So I have to backtrack to where I branched off. Is there any place else I can go? Well, sure. Now I can fall down to E. So I went A, B, C, E. Where does this go? Down to H. Now I hit a dead end because H doesn't go to anything. So I backtrack. Is there anywhere else I can go from E? No. Backtrack. Anywhere else I can go from B? No. Backtrack. Anywhere else I can go from A? Yes. I can go down to D. From there, I have a choice of F and G. So F comes first in the alphabet. Go down this way. Can F go anywhere? Well, it could go to E, but I've already visited E, so I don't want to visit again. So I backtrack. Go to G. Can G go anywhere? Yes, it can go to H, but that's already been visited, so I stop there. And so technically I would backtrack up to where I started, and there's no place else to go. So this is what we see in my printout from my program right here. So how does it actually do that? Well, let's look at that. So here's my depth first search function. So it gets a row number, and I'm going to start on the row for A. Here's the array. Here's my labels. And then here's my visited function, or excuse me, array, that indicates whether or not I've been somewhere. So I'm going to come down here, and I'm going to print the label for the row we're on, which is initially A. I'm going to indicate that I've been on this row, so I don't revisit this row. And then, and although I say row here, it's really, I visited node A is what that means. Let's just put that. And then I come down here and start working across, because notice that row was passed in, so row never changes. It's the column that changes. So I'm going to start moving along the columns, and this says that if this row column combination is not equal to 0, which means there's a connection there, and I have not visited it because I have 0, then I'm going to call depth first search again. So I'm using recursion. And the reason I use recursion here is so I can do the backtracking. Back over here. When I went to C and said, wow, I ran out of places to go, where did I just come from? It's the recursion that allows me to come back to here. If you haven't seen my recursion video, I encourage you to look at it. But basically the idea is I use the runtime stack of the computer to keep the status of where I left from. So when I call DFS again and go down to here, then on the runtime stack, there's an instance of the function in which I was processing node B, and so it knows that I left to come to here. But when I get back to that instance of the function, it'll go back to being B again. So if there's a path to follow to a node I haven't seen before, then I call def first search, giving it that column, which will be the row coming into it. So now I process that row and I start working across and do that. And so ultimately it backtracks enough to get back where we're at, and that's how I produce this. All right. So this is really all there is to it. Now what this would not deal with would be cases like this. If I had a disconnected graph, so I have these nodes and then I have some other nodes over here, say J and K, that can't be reached from any of these, I'd have to have some way of dealing with that. But this is the more typical case. All right? So that's all there is for an adjacency matrix. It's really just a two-dimensional array. And in this case, I would say it's an unweighted graph, although it is directed, but it's unweighted, so I just use zeros and ones to indicate no connection or there is a connection. So now see my adjacency list. So if we go back to my picture, which I can't find, come back to my picture, notice the way I drew this. I drew this thinking of linked list. So here's what I'm going to do. I'm going to have a file that contains source and destinations. So like destination 1, destination 2, and this will be source 1. And then we'll have source 2, and it has its destination 1 and destination 2, and so forth. So what I'm going to do is, this is a linked list of sources, right? So we'll say S1, S2, S3. That's a linked list. But then these, for the destinations, will also be a linked list. So destination 1, destination 2, the destination 1 for this, and maybe that's all there is, or so forth. So I'm going to build this linked list. Now, what information do I need to store? This would be a more complex structure than anything I've done before. So that means, up till now, we've got to buy with examples that look like this. Struct node, and maybe I just said something like int I, and then I said struct node star next, right? But now I not only have to keep track of the next source node, but I also have to keep track of the destination nodes. So what I do is I use one structure definition for this, because this has to go in two different directions potentially, and then I use something closer to this for the destinations. So let's see how I actually did that. Now this program, I will tell you, gets difficult to follow very quickly. And in fact, when I was trying to debug it, I had a number of problems. So in this case, I'm going to read this file. And so the first letter of each row is the source, and every additional letter is a destination node. So this says A goes to B and C, and B goes to A, C, and D, and so forth. So this graph is not the same as the one I showed you in the earlier example. This is more connected. All right. So it's the same thing I think that I have right here. Here's a picture that try to help you better understand it. Here's my pound define. So there's 8 nodes. And here's my first structure definition. So this is a source node, right? It stores a label as a character. So it will say it's node A or node B or whatever. And then I chose to treat the destination linked list kind of like a queue. So I'm going to have a head and a tail, and then I add new things to the tail end. But technically I never remove things, so in the strictest sense, it doesn't have to be considered a queue. And then for those destination nodes, then they simply just store what label they are and a link to the next node. So look at this right here, struct node star to one of these, but struct source node star, well, that's this. So this will be the address as I work my way down. So this goes from A down to B, down to C, down to D, down to E, and so forth. And then this right here, struct node destination head, is moving across. So this goes from A to B to C, from B to A to C to D, and so forth. If you're not confused yet, then you're not trying hard enough. Some functions. So part of this stuff here is just for reading the file. I create my pointers. I tried to give it somewhat meaningful names, but even then I still got confused trying to follow all this. Here I'm going to open up the file for reading. And then I'm going to start tokenizing. So if you've seen my other videos in which I tokenize, typically I would do this. All right? But now I call it source and destination. So source here is the address of a character, because in the first line of this file consists of A, B, C, terminating null. So source is the address of the A. So now I'm going to come down here and I want to add a node. And I dereference it. So what does that do? Well, if source is of type char star, then when I put a star on it, source itself is just a char, which means it's literally just the letter A. That's what I pass to this function. So let's see what the function looks like. So I say here, input is a single character. I'm going to allocate memory for this node. And I set the next, that is going down, I set that to null. Set the head, that's going to the right, to null. And then whatever the tail eventually will be is set to null. And then I store the label. And since it's not a string, I don't have to do a string copy. Since it's literally just a character, which is technically an int, I can do an assignment. So that was one of the benefits of passing in a single character instead of treating it as a string. I just do an assignment. So now let's go back to where we came from, was right here. And now I want to start working my way across to add B and C. So what do I do next? Well, if you've seen my queue video in which I talk about using a linked list to implement a queue, this is very similar. I have to distinguish between the very first node I add and any additional node that I add. And I do that here by, I'd set source head equal null right here. And so that way I know what's the first thing I'm adding. And so I'm going to add the first node, and then as I go down, so this actually is for the node containing the A and what I'm going to do. And then additional nodes will go down, so let's see what we have here. Sorry, I'm getting a little confused myself. Here's where I get the next letter, so this will be for B. So now destination is the address of the B. And as long as I'm continuing to get additional nodes on that row, this is keep going. So let me go back to this because I wasn't quite clear. This code here is for processing the source nodes going down. And since A is my first one, I want to do this. But when I add B to it, I'll do this because I'm adding to the tail end. And then C will be added there and so forth. So B, C, D, all the way down to H, we'll use this line of code. And then I'll update what the tail is. All right? So what does this do? Well, the logic's basically the same, except now I need to add a connection. So when I add a node, that's adding A, B, C, D, one of these. Coming back to my picture, these are my source nodes, and these are my destination nodes. Remember that. And so now I have a function for creating this kind of structure. So once again, I dereference just to pass the letter B, and then I'm going to say add a connection. So this is very straightforward. In fact, the code looks just like what I used in my previous linked list. Here, allocate memory for the node, set the next to null, store the data, which here is just a single character, and return the address to add to the link above. Just like before, this code is similar to what I did for queues. So if it's the very first node in the queue, I do this. Each additional node, I have to do this, and then I do this regardless. And then right here, I get the address for the next character. So in this case, it'd be the C. So I'd come up here, that's not equal to null. I'd add another node for C. That's my last letter on this row. So when I get down here, I get null. So this now will break because destination is equal to null. So I'll leave this loop. I hit this point right here, which means I go back up, get another line from the file, come down, do the same thing. Let's see what this program does. So it just prints out the results. Let's see how the printing works. So the printing is right here, and then I'm going to free memory. So how does this work? Print list. So here's my for loop. I don't need to initialize because head is already initialized for me. And then this head is not the head above, so it says as long as head is not equal to null, I'm going to print the current label that's stored in that node, which is A, and then I'm going to store the address for the first destination node, which is B, and then as long as I continue to have destination nodes, I keep printing labels. So I print B, then I print C. I run out of destination nodes here, so I'll print a new line, come back up, move to the next row, which is B, print the B, and then start processing the things B connects to, A, C, and D, and so forth. Do the same thing. In terms of freeing memory, it's very similar to that, except I don't really need to do any printing. And here what I do, let me fix this to make it a little easier to see. All right. I don't need to print the labels, but the rest of the code is very similar. So here, as long as head's not equal to null, keep moving down a row at a time and then process the rows. So what I'm going to do is I'm going to move across rows. So I need to free up B, I need to free up C, and once I've gotten rid of those, then I can free A. And then I come up and head becomes B. And then I'm going to work my way down. So I free A, free C, free D, and now I free B, and so forth. If you've seen my videos on either hash tables or linked list, or binary trees actually, but linked list in particular, you'll recognize a lot of the logic here. Now the variable names have changed, but the underlying logic is largely the same. I'm just working my way down a linked list and freeing nodes as I go along. So this program is much longer than some of the others, 171 lines of code, counting comments. But that's all there really is to an adjacency list, at least in the simplest case. So if you find videos like this helpful, please hit the subscribe button and let other people know if you think I've helped you out.